Okay, so last class we discussed about induction motor equivalent circuit, and then from the equivalent circuit we discussed about the different power relation, then torque relations, right? So then we found the expression for air gap power that is transferred to the rotor side, and then from there we found torque developed, right? Power developed and torque developed, right? Then by subtracting the constant loss or rotational loss from that, we'll find the shaft power, right? Shaft torque also you can find. So today we'll go further in this direction. So already we have seen all these expressions from the equivalent circuit, right? So no need to explain this. This is your exact equivalent circuit, what we have already discussed, right? Exact equivalent circuit. Like in transformer also we define exact equivalent circuit, then we approximate it. In transformer also we have approximate equivalent circuit, right? So why this approximation is required? Is it required the approximate equivalent? In transformer also we do have also equivalent circuit which we approximated, right? So what is this approximation and why we need this approximation? Because in order to simplify the calculation more, we can approximate assuming certain conditions or certain values in the circuit, right? So we can see here, we'll see the approximate equivalent circuit of induction motor. So this is your exact equivalent circuit. Now here you can see this current, which is, we call it I phi, magnetizing or exciting current, right? So that is nothing but it is equal to IC plus IM. So this IC is coreless component or coreless component of the current, and IM is your magnetizing component of the current, right? And now if we'll see, these currents are really small in magnitude because coreless component is very small and this resistance is very high, RC, and also XM is very high, the magnetizing reactance. Okay. So therefore your I phi is negligible as compared to, it is very less than I1 or I2. That means we can certainly say that I1 is approximately equal to I2, where if I'll shift this whole branch, this parallel branch to this side, and I'll move the R1 and JX1 to this side, then there will be very less error in this approximation, right? So we'll have very less error. So therefore less means it is very negligible error. So therefore we can very easily consider this approximation in order to simplify the calculations whatever we are doing, right? So this is now your approximate equivalent circuit, where as I told that your parallel shunt branch, that is consisting of core resistance or core loss component, that the resistance representing the core loss component, and the reactance that represents the magnetizing flux. So we'll shift to the left of the primary side resistance and leakage reactance. So then we'll have this equivalent circuit, right? Okay. So now this is your and we can see here how your calculation becomes easier more. So now we saw that I1 is, of course, I1 is equal to I phi plus I2, but whereas I2 is flowing in R1 and JX1, right? So now I can easily find here the expression for I2. Mathematically, if I know the equivalent circuit parameters, like experimentally you are determining the equivalent circuit parameter from your lab, right? By doing your no load test and Blocked-Rotor test, you can find R1 X1, R2 X2, right? We'll talk about that also in the later classes. So therefore I2 you can directly find just by saying that V1 by this sum of these resistances and reactances, right? Okay. So now I can find I2 is equal to V1 by Re plus JXC plus R2 into 1 minus S by S. So what is this Re? Re is R1 plus R2 and Xc is X1 plus X2. Okay. So Re is R1 plus R2 and Xc is X1 plus X2. Now this expression is correct. If we'll see applying KVL directly, I can write I2 is equal to V1. V1 is across this branch, right? This two. So V1 by R1 plus R2 plus JX1 plus X2 plus R2 by S1 into 1 minus S. So already we know this is your dynamic loading. This represents your dynamic loading of the motor, right? Okay. So now we know the expression for PD. Somebody is gossiping, I am hearing. Why you are gossiping? So PD is equal to PAG minus PRLC. Okay. So what is PAG? A PAG is your air gap power that is transferred through the air gap power from the input through the air gap to the rotor side, that is PAG, air gap power. And if we will subtract the rotor copper loss from that, we will have PD. PD is the power developed power, right? Okay. Now if we'll subtract from PAG, we know PAG is thrice of I2 square R2 by S. This is already we have derived in the last class, right? So this is your air gap power. And from this I will subtract the rotor copper loss, that is I2 square R2, thrice of I2 square R2, then we will get the power developed and we will get this expression, that is thrice of I2 square into 1 minus S into R2 by S, right? Okay. Now PD, if we'll now a little bit, I'll substitute I2 from this expression in PD, then I'll get this expression. Just by substituting I2 in PD expression, I2 expression is V1 by Re plus JXC plus R2 1 minus S by S, right? And just by substituting this, we'll get. So I hope everybody is getting. Manavendra is clarifying your doubts, maybe, right? Okay. So I2 is your magnitude of current. Okay, it is not a vector. So 3V1 square R2 into 1 minus S by S divided by this whole expression, whatever you are seeing here, right? Okay. So now this is your PD, and now I want to derive the maximum power criteria, right? So we know just by taking derivative of this with respect to S slip and equating to 0, I will find the maximum power criteria. Can you find it? Just take the derivative of and equate to 0 and find what is the condition, that means the slip at which maximum power occurs. Find the expression for slip where the maximum power occurs. Okay, so this will be your condition, right? So Re square plus Xc square equal to R2 by Sp into 1 minus Sp whole square. So this will get, then from this we can find Jd equal to R2 by Sp into 1 plus Sp, and Jd is the magnitude of the impedance Re plus jXc. Then we'll find from this expression Sp as equal to, that is the slip at which we'll get the maximum power is R2 upon R2 by Jd. Now if we'll substitute this slip here in the expression of power, then we'll get the maximum power developed, PDM. The expression for maximum power developed. So can you find it? Substituting Sp in PD expression, can you find PDM? Okay, if so, then let us see it. Correct. Okay. So everybody has got perhaps I think you will get it. So this is the answer, right? So 3 by 2 V1 square by Re plus Jd. So Jd is nothing but, here it is mentioned Jd, that is Re plus Jxc, the magnitude of Re plus Jxc. Okay, so this is your expression for power, maximum power developed from the approximate equivalent circuit, right? And now we'll see one problem. So this problem you need to do, kindly do this. Okay, so I hope everybody got this, Sp and PDM, because the equivalent circuit is given, right? So Z1 is given, R1 plus Jx1 is given, right? And Z2 is given, R2 plus Jx2 is given. So you need to find first the slip, not slip, sorry, you have to find the frequency, right? And frequency is given, frequency is given. So you need to find, directly you can substitute Sp, expression of Sp is, what is R2 by, what is the expression? R2 plus Jd, okay? So you can substitute and find it out. And then similarly PDM also you can find. And if you want to find the torque, you have to divide PDM by omega s. Okay, omega s you can find from the given data, that is 60 hertz, 6 pole. So you can find 120 F by P, then you convert it to omega, right? Okay, I hope everybody understood. And when you are substituting this voltage, this is a line to line voltage, right? You need to make it to phase voltage. Okay, so now we'll find the maximum torque criterion. So PD expression already we know, this is your developed power expression, right? Already we derived this. Now we know TD is torque developed will be equal to PD by omega m. So omega m is nothing but omega s into 1 minus s. So I can write PD by omega s into 1 minus s. So then after substituting the expression of PD here from this expression, then I will find the TD expression. So TD will be equal to, just 1 minus s will be cancelled out and omega s will be divided, or rest of the expressions will remain same as PD. So this is the expression for the developed torque on the shaft. Okay. So this is the expression for developed torque on the shaft. Now from this expression I need to find the maximum torque criterion. That means I want to find the slip at which the maximum torque will occur, that is known as breakdown torque. So can you find the slip at which the maximum torque will occur? Just similar process will follow. Just take the derivative of the TD with respect to s and find the slip at which the maximum torque will occur, right? That means I will take the derivative of TD with respect to s, equate to 0. Then I will find the expression of s from this, and that will give me the expression of Sv. Can you find the expression of Sv? Okay, let us see the answer. So this is your slip at which the torque will be maximum. R2 upon, little bit you are correct, but it will be not the whole square root. R2 by R1 square plus X1 plus X2 whole square root. So please do the homework. Prepare for the exam. This you have to do. Okay. Okay, so this is your maximum torque criterion. So where the torque will be maximum, TD. So after substituting this SB here in TD equation, we'll get the maximum torque. Okay, the expression for maximum torque. That also you can do. So you will find this TDM, the expression for TDM will be 3 by 2. Same expression almost like PDM, but it is little change. The 3 by 2 is same, V1 square is same, but except that R1 plus R1 square root of R1 square plus X1 plus X2 whole square, right? And SB we know here, this one is SB. So now what we are observing from these two expressions, one is your torque, maximum torque equation, and your breakdown slip. That means breakdown slip, when I will mention anytime breakdown slip, that indicates that slip at which the torque is maximum. Okay. So the breakdown slip, what we are observing here, is directly proportional to the rotor resistance. Right? Okay. But we know the rotor resistance can be adjusted in case of wound rotor motor. You have seen wound rotor motor in your lab? Not seen? Wound rotor induction motor. That is slip ring induction motor. Okay. So don't confuse. Wound rotor is equal to slip ring. Okay. Wound rotors means the rotor is wounded. It is not squirrel cage. Okay. So that is wound rotor slip ring induction motor. That is also sometimes called slip ring induction motor because two slip rings are there in order to insert external resistance to the circuit. Okay. So that therefore it is known as sometimes slip ring induction motors. So therefore it is very easy to insert external resistances to adjust the slip here, right, where the maximum torque will get. We can easily adjust it. Whereas if we will see the expression of maximum torque, we will not find any term of R2 here. Are we seeing any R2 term in maximum torque equation? There is no R2 term. That means this maximum torque is independent of the resistance in the rotor circuit. Whatever resistance you put in the rotor circuit doesn't matter, the maximum torque will remain same. It will not change. Okay. So therefore, at the starting also we can have maximum torque in this case, like in the slip ring motor. At the starting, by adjusting the external resistance in the rotor circuit, we can get the maximum torque when we will fulfill this criteria, right? So under starting SB equal to 1, right? So if we'll put 1 here, then I can find R2, the value of R2 in terms of R1, X1, X2, and I can simply add the external resistance in the R2, a rotor circuit, then I will get the maximum torque in the starting. Because there are many applications where we need the highest torque of the induction motor at the starting point. But not in case of like your fan, we don't require highest starting torque. Like in case of traction motors, we need high starting torque during starting. So therefore this is very useful, right? So maximum torque developed by a motor is independent of the rotor resistance. That means the motor develops the same maximum torque regardless of its rotor resistance, right? So the rotor resistance affects only the breakdown slip, as we can see here, this expression, right? Or the breakdown speed at which the maximum torque occurs. So what we are seeing here, the torque versus speed characteristic, per unit speed. torque versus the per unit speed. And with varying rotor resistance, we can see the maximum torque remains constant at this peak. Okay, this is your maximum torque, EDM. It remains constant even if we are varying the rotor resistance, but we are getting the various speed at which we get the maximum torque. Sometime here 0.5 per unit, 0.75 per unit, 0.85 per unit, like this we get. But your maximum, the magnitude of the maximum torque is remaining same. But the speed at which, if we'll change the rotor resistance, what we are getting? We are getting the speed at which the maximum torque occurs, but the magnitude of the maximum torque remains same, right? And we know the slip at which the maximum power occurs, that is R2 by R2 plus JD, and SB is this, right? So from these two expressions, if we compare SP and SB, SP is the slip at which we get the maximum power, and SB is the slip at which we get the breakdown torque or the maximum torque, right? If we compare these two expressions, what we are seeing here, SP is having a larger value in the denominator side, right? Here we have JD term, which is actually much more larger as compared to the denominator of the SP. That means it indicates that the slip at which the maximum torque occurs is always greater than the slip at which the maximum power occurs, right? So therefore, the motor develops maximum power at a slip lower than that at which it develops the maximum torque. That means SP always less than SB, right? So then we'll see further approximation in this. What further approximation we can do? And again, if we take further approximation to our this already we have discussed, and further approximation is that where we'll assume that the impedance of the starter is negligible as compared to the rotor impedance. Okay. When the starter impedance is small, it can be neglected in comparison with the rotor impedance at standstill condition. So under standstill condition, because we know under standstill condition the impedance of the starter is very small. If you have done the Blocked-Rotor Test and you found it, you might have seen or observed it, right? So therefore, under that condition, your breakdown slip or slip at the breakdown torque will become, just put R1 equal to 0, just substitute R1 equal to X1 equal to 0 in the expression of the slip equation. You will find R2 by X2. This is the most simplified expression. When you neglect the impedance, starter impedance, we'll get the most simplified expression for breakdown slip at the breakdown torque, that is R2 by X2. And this is how you were asked in your lab test also. In many people you might have faced that, find the external resistance in the rotor in 80% of the maximum torque. We'll come to that, okay, gradually. So this equation, in fact, what it states, that breakdown slip is simply a ratio of rotor resistance and rotor reactance. So therefore there is no need to find out any parameter of the starter. Only you need to do the test at the rotor side. Very simple. Just put one wattmeter, ammeter, voltmeter. You can find resistance, reactance, right? And just do it. So when the rotor resistance is made equal to the rotor reactance, the breakdown slip is unity. So when I will make it R2 equal to X2, then your SB will become 1. So this slip becomes 1 under what condition? When the motor is about to start. That means when rotor is at the standstill condition, right? So that means under starting condition we get the maximum torque when R2 equal to X2. So this is the condition where we can get the maximum torque at the starting, right? So therefore the motor develops maximum torque at when R2 is equal to X2 at the starting condition. So now your torque equation, we know this. Now if we'll simplify the torque equation considering the small impedance in the starter, we'll find this expression. Just substituting R1 or neglecting R1 and X1, we'll find TDM, maximum torque expression, as 3Vn. Just from this equation, we'll get this equation 3V1 square by 2 omega s 1 by X2. So instead of X2, I can also substitute in terms of slip, breakdown slip. That will be X2 will be equal to, from this expression, R2 by SB. So if I'll substitute here, it will become 3V1 square by 2 omega s SB by R2. Okay, so this is a expression for maximum torque, and the breakdown slip is here SB, and that breakdown slip is R2 by X2. Okay, so now your current expression, if we'll see, if I neglect the starter impedance, then I will find this expression. I2 is equal to V1 by R2 by S plus JX2. Now if I will find the expression for torque, developed torque, by neglecting the starter impedance, I will find this expression 3I2 square R2. This is the expression. If I will substitute I2 here, then I will find 3V1 square by R2 by S square plus X2 square into R2 by S of omega S. So this is a torque expression, general torque expression for any slip, under any slip condition, right? And now we know the expression for TDM, that is the maximum torque developed. Now if I will take the ratio of general expression of torque TD under any slip and the maximum torque, which is the breakdown torque, happens in breakdown slip. If I will just take the ratio, I will get this expression TD by TDM. Just little manipulation if you will do, you will find twice of S into SB by S square plus SB square. In fact, in your laboratory experiment, this expression you need to use this expression to find the external resistance, and how it will be, I will explain it. Okay, so this is a very useful. Those who have not performed, tomorrow they have lab exam, they should be ready for it. Okay, this is a very useful approximate relation, and it can be used to determine the torque developed at any slip S once the breakdown torque TDM and the breakdown slip SB are known. If we know this TDM, somehow we can calculate, or we know, and SB we know, then we can easily calculate the torque at any slip, whether it is starting or whether at the no load condition, any slip we can calculate this torque if we know TDM and SB from this expression, right? Okay. Now let us move to this example. This example will help you in tomorrow's lab exam. Those will get the experiment of this. Okay, now we'll see the maximum efficiency criterion. We saw till now maximum torque criterion, and maximum efficiency criterion we can find. So we know if we'll consider the core loss, which is included in the rotational loss. Core loss is a constant loss, and we can include it in the rotational loss as well. Both, by adding both together, we can say it is a constant loss. Then your input power, I can write it as 3V1I2 cos theta to the induction motor. Then your output power will be input power P in minus copper loss, P starter copper loss minus P rotor copper loss. Okay, then minus PR is the rotational loss, which includes the core loss as well. Okay, this is your stator copper and rotor loss, this is your rotation loss. Okay, now if we'll write the expression for efficiency, it will be like this. Efficiency will be P out by P in. So this is your expression. Now can you find the current, or can you find the expression or the condition for which we will get the maximum efficiency, eta max? Okay, under what condition? To take the derivative of this expression with respect to I2, because I2 is here only variable, so equate it to 0 and you will find the criterion for maximum efficiency. Can you find it? Please find it. Equivalent circuit parameters, which already you have done it in your lab, right? Equivalent circuit parameters you have done, right? What are the tests you have done in your lab for finding this equivalent? OCC कहाँ आ गया? OCC क्या है? हाँ, no load test, then Blocked-Rotor test, और कुछ क्या है? नहीं क्या कुछ? रेजिस्टेंस फाइंड आउट करने के लिए एक रेजिस्टेंस टेस्ट करते हैं, ठीक? Multimeters, yes, very good. So we now see the tests which we conduct generally on induction motor to find out the parameters. One is your resistance test, starter resistance test, then Blocked-Rotor test, no load test, and load test. Load test is just to find out the efficiency. So the starter resistance test is this. We connect across two terminals. If it is Y connected, then if your measured value is R, then for Y connected motor, R1 will be 0.5 into R. Okay, and for delta connection it will be 1.5 into R. I hope everybody understands this. Okay, now for the Blocked-Rotor test, this is your machine. You put wattmeter, voltmeter, and ammeter, and what you do here, first you block the rotor, it should not move. Then you apply the voltage here in the three terminals, okay, by just increasing it through the auto transformer, three-phase auto transformer. And when the rated current flows, then we take the readings of voltage, voltmeter, ammeter, and wattmeter. And what will be the voltage we read under Blocked-Rotor test? How much? It will be very less, maybe around 6% of the rated voltage, right? Very less. And current will be rated current, right? And in fact, what happens here through this test, you can find the equivalent resistance and equivalent reactance. Okay, that means your R1 plus R2 and X1 plus X2. Why not your parallel branches like your RC and XM? RC and XM cannot be found from this test. Why? Because the voltage applied during Blocked-Rotor condition is very small, and because of that voltage in the parallel branch, the current flown will be very less, and through which we cannot determine the actual values, right? So therefore it cannot be determined through the Blocked-Rotor test. And under Blocked-Rotor test, what is the value of S, your slip? What is the value of slip? 1, right? So if we'll put the dynamic resistance across, the dynamic resistance was R2 into 1 minus S by S, right? If we'll substitute 1 here, it will become 0. Okay, what it indicates? It 0 means? 0 means the dynamic resistance becomes 0 means it is sorted, right? Sorted. So therefore we'll remove this dynamic resistance now, and we can draw the equivalent circuit like this by sorting the terminal here. So now your equivalent circuit under blocked rotor condition will look like this. Okay, very simple. It is sorted. Now only we have R1, R2, X1, X2, and whatever voltage we are applying here, whatever current we are measuring, and whatever power we measured, from that we can find easily R1, R2, X1, X2. I hope already you have done this in your laboratory, so no need of further explanation. Is it required? Anybody requires further explanation? No. Okay. So now we'll see the no load test. Okay. In no load test, what we do? The same connection, but we allow the rotor to freely move. The rotor moves freely till it attains the not synchronous speed exactly, but about to attain the synchronous speed, right? Under this condition, what will be the value of slip? It is approximately 0, right? Okay. Now under this condition, your dynamic resistance, what will be the value of this? Infinite. So as soon as it becomes infinite, so it will act as open circuit, right? Therefore the equivalent circuit we plot here, it will be open circuit. Open circuit means only the current is flowing through this, and we apply here rated voltage, and we find this RC and XM through the measuring the current, voltage and wattmeter readings. Okay, very simple. So now you found the equivalent circuit parameters: RC, XM, R1, X1, R2 and X2. So your experiment is over, right? So now we see the load test, of course, is there for finding efficiency. No need to discuss further. Okay. So then we'll see the starting of the induction motor. What is the problem in starting the induction motor? We have previously seen the problem in case of starting the DC motors. What is the problem? The problem is the high current. Okay, high current, because in DC motor what happens? Why the high current flows? Back EMF is not there, right? But here in case of induction motor, what is the problem? During starting condition, what is the problem? We'll see here from this. Under starting condition, what happens? We'll see. So under starting condition, the current I2 will be V1 by Re plus Xc, because this will become 0. Okay. So therefore, it will be V1 by Re plus Jxc. Okay. V1 by Re. Re is your R1 plus R2 and Xc is X1 plus X2. Then TDS, if we'll find the starting torque here, what will be the value? It will be 3, just substituting I2 in the torque equation, we'll get 3 V1 square R2 divided by omega S into Re square plus Xc square, right? Now what the problem we face is that the voltage, maybe it is 440 volt or whatever, power phase value maybe 230 volt, and these resistances and reactance values are very small. Unless this dynamic resistance is present, which actually gives a high value of resistance under the rotating condition of the motor. But when the rotor is not rotating, this dynamic resistance becomes 0. So therefore, your current in the starting becomes very high value. So it increases. So therefore, because of this high value of current, immediately on the starting condition, we get a high starting torque, much more than the maximum starting torque, which is not actually very useful, that rather it will break the rotor. Okay. So therefore, it is essentially not required to start with this condition, the motor, like directly supplying the voltage or directly switching on the voltage to the large induction motors. Small induction motors like a fan you can do, start it, but not the large induction motors. Okay. Above 5 HP also we cannot start. Yes. We put auto transformer. Yes. Okay. So therefore there are various methods devised in the literature also, we'll find in the books like auto transformer, there are delta starters, there are many methods which actually minimizes this voltage during starting, this input voltage during starting condition, right? So by this some of the methods are there, we are not discussing in detail. Like one method you are doing in your laboratory, that is simply by starting from 0 voltage, gradually enhancing it to the rated voltage, right? So that is one method. Now I'll talk about little bit the speed control of the induction motor. Why the speed control is required? Because of from the industrial aspect or industrial point of view, like fan, we need to control the speed by regulator, right? We are doing control of the speed. So similarly, in the industry also we need to control the speed of the motor for various applications. So how we can control? This is your expression or equation for the speed, right? 120F by P into 1 minus S. Okay. So on what it depends the speed? One is your frequency, right? Okay. If we will increase the frequency with constant value of number of poles, then you can get increased speed, right? Similarly, it depends upon the number of poles as well. If our frequency is maintained at constant value, if I can change the poles dynamically inside the machine, then I can get the speed according to my digit, right? So these are the two methods generally employed. One is your changing the frequency, because we have cycloconverters nowadays in power electronics. So using that, we can change the frequency. We can get the variable frequency, and through which we can control the speed of the motor, and also by varying the poles, number of poles. Okay. So therefore, speed of an induction motor can be controlled by changing the frequency of the applied voltage source and or the number of poles. Okay. Speed can also be controlled by either changing the applied voltage, the armature resistance, or introducing the external EMF in the rotor circuit. It is also happens in case of slip ring motor. Okay. So this is how we do the speed control of induction motor. Okay. So we'll stop here, and this is the end of your course. Okay. Thank you very much. So now